There was a request in one of the comments on my earlier videos to review a paper that analyses the motion of the UAP in the FLIR video, as this paper seems to contradict the conclusions in my video. This is the paper. Estimating flight characteristics of anomalous unidentified aerial vehicles. I also found this second paper that does a similar analysis on the same subject. A forensic analysis of Navy Carrier Strike Group 11's encounter with an anomalous aerial vehicle. Both these papers cover other aspects, but I'm going to focus on the parts that analyse the FLIR UAP motion, as I did in my earlier video. In the first paper, I'm looking at page 11, section 243, at FLIR video. This section examines the last 32 frames of the video, largely overlapping with the frame-by-frame analysis that I did in my video. They use a version of the FLIR video that's been modified, so the pixel values they quote are different to mine, but it's essentially the same video, and it's easy to correct for the different video scales. Let's take a quick look through this section. They say, we examined the last 32 frames of the Nimitz video, in which the Tic Tac UAV accelerated to the left. There's already a clue here that they've got a conclusion in mind before they've started. As the object of the analysis is to assess how the object behaved, it seems a little premature to assume this at the start. They say the FLIR orientation was fixed at a zenith angle of 5 degrees above the aircraft axis and at an azimuthal angle of 8 degrees left of the aircraft axis. This is an assumption and is important as it leads them to the conclusion that follows here. The apparent motion of the UAV in the video frames is attributable only to the physical motion of the UAV, and the UAV can be treated as if starting from rest with respect to the aircraft. The FLIR was not at rest with respect to the aircraft for most of the video, but was in motion. We know this because the aircraft is flying straight and level, but the bearing to the UAP is changing throughout most of the video. The critical point here is that the FLIR was moving, then it's assumed to stop. But when did it stop, and does a different assumption about when it stopped affect their calculation? The resolution of the bearing is only to the nearest degree, so we can't say definitively when it stopped. To track the position, they say this. We concentrated on tracking the position of the right edge of the UAV. In this section they say, the UAV was estimated to be at least 40 feet in length. This size estimate seems to be taken from the testimony of the Tic Tac encountered by Commander Fravor, but we don't know that this is the same object. The encounter was not in the same location as the Fravor encounter, so this size assumption is questionable, and the size is fundamental to their acceleration calculation. Even if we accept the size assumption, there's also another assumption here that the IR image shows all of the object. I suggested in an earlier video that this is not the case, by comparing the IR and the TV images from earlier in the video. There seem to be many assumptions that are not really justified that could affect their estimates of acceleration. Some may be minor, but some are definitely fundamental. Let's look at some of their results. Here they say, figure 6. The figures A, B, C and D illustrate the position of the right edge of the UAV in pixels. I've corrected for the different video scales and compared this analysis with my analysis. As you can see here, it's very close, so I'm happy that both techniques for determining angular position are adequate and give similar results. The video scale and using the right edge instead of the center is not a serious problem. For their analysis, they say, we consider several different kinematic models. Several models are considered, but not a model where the UAP is moving at constant velocity. That model is precluded since they assumed that the UAP is initially at rest, but that assumption has not been justified. We see that Model 4 is the most probable solution. Model 4 is an initial acceleration of around 76 g, followed by constant motion. I haven't checked their analysis, but I have no reason to doubt that they've done the calculations correctly, and out of the 4 models they assessed, and based on their assumptions, Model 4 could be the most probable. However, the assumptions are absolutely critical here. If the UAP is not initially at rest, and their initial 76G acceleration is actually caused by the FLIR movement, then their calculation is not valid. You can see that the constant velocity part is just a rough straight line fit through the data points, exactly as I did in my analysis. Before I make any conclusions about this paper, let's look at the second paper. I'm looking at Appendix J, page 195. Acceleration, speed and power calculations based on the FLIR video. I'm just going to focus on the acceleration calculations. This paper uses the same video as I did at the original size. Conveniently, this paper lists some assumptions up front, so we don't need to dig through the paper to find them. I'll go through the key ones for the acceleration calculation here. First of all, assumption 3. Any object that has a long axial dimension, as it would turn left, would appear to change in size on the FLIR display. The author believes this is a powerful argument against this being a conventional airframe of any known type. That might be one possible interpretation, but equally, using the same logic, you should consider that as possible evidence that the UAP is not turning. As we don't know that the whole of the object is shown in the IR image, I think that both conclusions would be speculative. Assumption 4. The apparent movement of the tic-tac is due to the tic-tac moving to the left and not due to the airplane moving to the right. This is based on the FLIR display showing that the tic-tac remains in a relatively stable position, as the FLIR display registers a constant angular position at the top of the FLIR display of 8 degrees to left and 5 degrees down. Here we have the same assumption as in the first paper, and it's the critical one. Actually, this paper recognizes that this assumption is absolutely critical and could be wrong, even eventually emphasizing this with underlined text. They say, the tracking servo does not seem to change its position, but it is possible that a small angular degree shift of a few tenths of a degree would not be registered in the display, as the display does not appear to update changes of less than 1 degree. This is what we previously noted, and means we can't be sure when or if the FLIR stops moving. They conclude, underlined, this could result in what appears to be a large acceleration, and not due to any change in the object's motion. This would also nullify assumption 3 above, as the object would not be turning to the left and no change in shape would be observed. So they recognize the importance of the lack of resolution on the azimuth display, which means movements of a few tenths of a degree would not be registered on the display. They don't point it out here, but remember the whole display is only covering a few tenths of a degree, only 0.35 degrees in 2 times zoom. So movement across the entire display could be caused by FLIR movement with no change in the display to indicate it's moving. Having recognized the criticality of this assumption, they then justify the assumption that the FLIR is stationary by saying that the FLIR display would be very difficult for the pilot to use if small angular deviations due to atmospheric vibrations would constantly make objects on the display shoot off the screen. So they consider and rule out inadvertent motion due to atmospheric vibrations. But as in the previous paper, they don't consider the fact that the instrument moves and stops itself as it tracks. This is a significant omission, especially considering that the FLIR has clearly been moving for most of the video up to the section that they've analysed. Again, I won't go through the calculations in this paper. They're likely to be correct as they use a fairly simple calculation approach. The problem is that the mathematics in both papers are based on a highly dubious assumption, which the second paper pointed out is critical, but didn't adequately justify. Both papers calculate acceleration of the UAP as if it starts from a stationary position, but don't investigate the possibility that it is never stationary. They also rely on an assumed size of the object to calculate acceleration, but the size is not derived from this video, So even if the other assumptions are correct, the accelerations calculated are questionable. I don't dispute that the calculated accelerations might be one of the possible motions that would result in what we see on the video, but it's not the only one. I show in my earlier analysis that there is also another possibility, that the object is something that is moving in an entirely unremarkable way, and no laws of physics or engineering have to be broken to get exactly the FLIR video that we see. The problem with both papers is not really the correctness of the mathematics, but the lack of justification for critical assumptions, and the lack of recognition in the conclusions that many other possible motions exist. Paper 1 confidently states that we have shown that these objects cannot be of any known aircraft or missiles using current technology. And paper 2 also confidently states it cannot be any type of aircraft using current technology. I think I've shown in my analysis that the object could be something entirely conventional. It's not possible to say definitively that the UAP did not accelerate rapidly, but lack of proof that it didn't is not proof that it did. What we can say is that one plausible explanation that fits the motion we see in the video is an object moving at a roughly constant speed from right to left. As usual, I'm happy to be corrected, so if you see any problems in my logic, let me know in the comments. I think I've exhausted this video now, so I'm planning to take a closer look at the gimbal video next. Subscribe if you want to be notified when I post the next video.